Okay, we will start from last class we looked at the typical resistance spot welding thermal cycle, right. So, we looked at a simple thermal cycle. What we have looked at it is say for example current, or it can also be load. It is also important, right, to keep the two faying interfaces together. So, basically cycle looks like, so we will start first loading. The moment we achieve a required load, and then the current will also start forming. Okay. So, load cycle will be something like this, and then the current cycle. So, if you look at, if you take a red one, orange one, so then you will have a current cycle going something like that, okay, right. So, typically the current will be in few kiloamperes, okay. So, for so 1.2 mm thick. So, why always I use 1.2 mm, right, even for filler wire and for sheet. These are very commonly used thicknesses and diameters for any engineering applications, especially for automotive industries, right. So, I pick up 1.2, which is my favorite thickness to an experiment. So, 1.2 mm thick steel, we use about 4 to 8 kiloamperes based on the weld nugget size what we want, okay. So, the the load would be in somewhere so around few thousand kilonewtons, newtons or kilonewtons, 3 or 4 kilonewtons, depends, okay. So, that is a typical the current and then load we use, and this is a very simple thermal cycle, okay. So, this will do a job for us, but we always greedy, right, and we will have to modify various for example thermal cycles. You want to introduce a pre-weld heating or a post-weld heating, and in some cases it is important to raise the temperature more gradually or more at a very slow rate, okay. So, in that case, and this simple weld thermal cycle may not give you the freedom to play around with the welding parameters, for example heating rate, cooling rate, or holding time, for example, or if you want to introduce a post-weld heat treatment, you can also do it here, same weld thermal cycle. So, apply in a post pulsing, okay. So, you will have a second current pulse which can go like that. So, that will give us like sort of a post-weld heat treatment. So, the various possibilities can be achieved by modifying the current and the load, the cycle what we apply while applying typical weld thermal cycle, okay. So, in order to achieve the typical weld thermal cycle, we also need to understand the characteristic of a material as a function of current and load, okay. So, characteristic by meaning the ability to melt, right. So, for example, for a given thickness, what factor determines the delta T, the change in temperature, right. So, for example, if you want to increase the temperature of material from 600 to say 1500, okay, and what do you need to know, so that you can give a certain amount of energy, so that you can reach the delta T. Come on guys, you understand my question? No, right. So, for your material, so material of A, right. So, this material now we are in room temperature say 300 Kelvin, and you will have to rise the temperature to say 1580, or we can say that 1800 Kelvin. How do you calculate how much energy you need to achieve this increasing temperature, delta T? Yeah, exactly, you need to know specific heat capacity, right. So, delta T would be, how do you calculate delta T? So, Q is mCp delta T, right, isn't it. So, this is the definition of specific heat capacity, isn't it, right. The Cp is, what is unit of Cp? Joule kg per Kelvin, exactly. So, what you need is, we need to know how much amount of J goes in, right, to know the required delta T. So, this will be delta T will be Q divided by mCp, right. So, now if you want to know how much Q you need to rise delta T, so you need two factors. So, one factor is Cp, so that is a material parameter, okay. And then the other only factor which determines the heat generation or heat required to increase the temperature from say a room temperature to melting point is the mass, isn't it? So, mass here we define the mass in terms of thickness. Okay. Say for example, if you have 1.2 mm thick, so we know the active volume is defined by the cylinder. Cylinder diameter will be the electrode diameter, isn't it? The height of the cylinder would be the combined thicknesses of the sheet, isn't it? So, suppose if you have 1.2 mm, so you have an electrode something like this, and then you place 2 sheets and then bottom electrode. So, you apply load, isn't it? So, we all already know the Q is I square R T, exactly. So, now we need to know delta T, isn't it? So, how do you calculate delta T? Q you can know if once you know R4 or R3 the contact resistance, we can measure the Q. We know say for example given time and a given current, right. Suppose if you want to know how much energy is needed to rise the temperature and so, only factor we know is the M. So, M you can assume or you can calculate, assuming it there is a cylinder which is actually heating up. What is the height of the cylinder? The combined thickness of the sheets. So, once you know the cylinder volume, you know density of the material, you can calculate M. What is the volume of cylinder? Pi r squared h, isn't it? So, you know R which is electrode diameter, electrode radius, h is the combined thickness, isn't it? So, once you know the volume of that cylinder, you know density of steel or any metal alloy you are using it. So, then you can calculate M. So, once you know M, Cp is given, okay, and delta T is say for example, you need to rise the temperature from room temperature to melting point, then you can calculate the Q needed. So, once you know the Q amount of Q is needed, then we can back calculate what will be the current you want to use, right. So, we know the contact resistance. Once you know the contact resistance, then as a function of time you can measure or you can get the current. It's clear? So, this is how we develop the welding parameters to get a diameter equal to the weld nugget diameter, right. So, as a thumb rule, the typical weld nugget diameter is always 4 times square root of thickness. Okay. So, if your thickness is 1 mm, the weld nugget diameter is acceptable weld nugget diameter is 4 mm. Okay. So, 4 mm means if you take a cross section, basically, so it will be like this, isn't it? So, ideally you will get an average diameter. So, if this is 1 mm, so you need to achieve 4 mm weld nugget diameter at the center axis of the weld. So, this is the weld cross section. Okay. So, now we can calculate once you know the thickness, the required diameter, how much current is needed for a given time of welding, isn't it? So, we can use our physics to calculate the welding current and time is needed to achieve a required weld nugget diameter. It's clear? Yes or no? Okay, good. So, then once you do all the calculations, so we can also establish what is known as weld growth curves. Okay, so, weld growth curve is plotted as a function of current or welding time and then weld nugget diameter I or T as a function of nugget diameter. Right, and this is for a given thickness, because if you change the thickness, M changes, isn't it, right, and then this curve will change. So, obviously, so for a given thickness and given material, because if you change the material, Cp changes, right. So, by fixing the thickness and then Cp, we can develop weld nugget diameter and then as a function of current and then or by fixing the time we can get the current, isn't it, or by fixing the current you can get the time, because those two are independent variables. Clear? So, we can develop the well nugget diameter. The curve generally looks like this. Okay. So, there is a one current at which, so we cannot form any well nugget, because you form so much of liquid, then if you are applying a load, liquid get expelled. So, that is the current at which the expulsion happens or splashing happens. That current is known as the I max. The current, sorry, this is I max. And this is the maximum well nugget diameter that you can form. Okay. Okay, so we will see in detail all these concepts what I explained today's class, right? It's clear? Good. So, we will move on to the slides. Any questions so far from last class? No? Good. Go ahead. So, it is a typical simple well thermal cycle in order to achieve it, and this is how we do. Okay. So, simple well thermal cycle I showed you in the previous graph, simple current and then a load applied over a time, isn't it. So, what do we do in a simple thermal cycle? So, there is a skews time, so load is increased. Okay. So, the moment you achieve a required welding load, then you start passing the current, right. So, during this process you can keep the load constant, and then upon applying a welding current over a welding time, and then you switch off the current and release the load, that is it. So, this simple well thermal cycle can give us the required current needed for generating a well nugget diameter, right. It is clear. So, the important the components of this entire well thermal cycle is the skews time, weld time, hold time and off time. So, the entire welding cycle would run not more than 200 milliseconds in a typical resistance spot welding, right. It is clear. But this is extremely simple. In real life, such a simple well thermal cycle we hardly use. Okay. So, we will have to introduce a lot of modifications. For example, you know that some alloys in say for example highly alloyed steel, you will end up getting only martensite upon cooling, because the cooling rate here, as I said, can go thousands of kelvins per second. Okay. So, it is very difficult to achieve other than martensite microstructure, okay, during welding. So, we may have to do a tempering treatment, right. So, what do we do? So, we do a second pulsing or a post pulsing upon welding time, so that you cool to room temperature and then subsequently you add an additional pulse, so that the martensite is in the weld zone is getting tempered. Okay. So, we can also program that in the weld cycle itself, or you can also reduce the cooling rate by using a preheating. So, instead of taking a temperature directly to room temperature, you may also have a pre-pulse, a pulsing before the actual welding pulse. So, that means that you are preheating the interface to a temperature of say 400 degrees centigrade. So, that may reduce the temperature gradient, and subsequently it can also reduce the cooling rate. Okay. So, in real life, if you have an advanced resistance spot welding equipment with a good PID control. So, what is PID? Yeah. So, the mechatronics guy should know about it. So, if he does not know, then you have a problem. So, these are all the professional integration and differential control. So, these are the input output feedback control mechanism. So, any resistance spot welding equipment would have a PID control to program a very complex well thermal cycle. Okay. So, it is an enhanced well thermal cycle what we use. For example, so you may have a loading cycle, something like that. So, where you have a skews time where material is just squash, and then you may have a preheating. So, preheating is achieved by applying a small short pulse. So, you may not use a current pulse of a well thermal cycle where it will be few kiloamperes. So, you may use say 800 amperes or so. So, that the temperature is reached about 400 to 500 degrees centigrade at the interface. And subsequently, we can also ramp up the current slowly, okay, instead of having doing an immediate ramp up to a maximum 5 kiloamperes. So, you can also slowly increase the current such a way that material also heats up reasonably slow heating rate in order to avoid the stress development in the material. And then during this process you can also apply a well time, maintain it, and subsequently you can also slowly decrease the current in such a way that you maintain a cooling rate, right. And you may also increase the load upon cooling. It is also beneficial because in order to mitigate the residual stress that is forming during welding, say when the martensite forms. So, you have a tensile expansion, and you can also accommodate that by applying a compressive force. Okay. So, in order to reduce the residual stress development in the weld, so you may also play around with the subsequently when the weld nugget is cooling down to room temperature, you may also increase the load in such a way that you apply a compressive force to mitigate the tensile stress that is developing in the microstructure, right. It is clear. So, in an enhanced thermal cycle, typical thermic cycle, you have a squeeze time and then a preheating time and the upslope time and then actual welding time. And in this welding time also, we can also have an in between a cooling time, okay. So, that is also possible. Okay. So, you may also introduce an intermediate cooling, so that you do not really increase the cooling rate and significantly, and then subsequently you can also change the cooling rate upon welding, okay. And then you have squeeze time to keep the stress, the compressive forces applied when the material is cooling down to room temperature, and then subsequently you can also apply a second start pulse post weld in order to heat up the weld nugget to a temperature where you expect the martensite to get tempered, right. It is clear. So, these kind of complex weld thermal cycles are commonly used for engineering applications, so that we can mitigate the microstructure development and the stress that is developed when you are welding in an overlap configuration, right. And the modern resistance spot welding equipment, all of them are capable of generating such weld thermal cycles. And it is extremely important because if you look at welding metallurgy of the automotive steels, okay, so it is difficult to achieve good mechanical properties without any post weld heat treatment, okay. So, it is extremely important to use a post pulsing not only to temper the martensitic microstructure, also to homogenize the elemental segregation that is happening in the microstructure. Otherwise, so if you look at the typical cross sectional overview of a resistance spot weld, so this is the two sheet, okay. So, this is how you look like in resistance spot weld, and you have weld nugget here, is not it, the cross section. So, this is a weld, and if you look at a typical resistance spot weld, you always have a notch at the weld center line. So, when you are trying to pull the tensile loading, so it is like a notch, and then if you have very strong segregation of alloying elements at the weld center, and this notch would act as a stress concentration area, and then you will end up forming a crack going towards the weld center line, because weld center line is the highly segregated area, that is the area where it solidifies at the end, okay. So, you expect an alloying element segregation make this weld center line very brittle, okay. So, in order to avoid the weld center line segregation, so you may also this post pulsing can be very helpful, because this is like a heat treatment, homogenization treatment. So, after forming a weld nugget, you form a subsequent pulse in such a way that you can homogenize the whatever elemental segregation happens in the weld center line. We will see in detail when you move along. So, the post pulsing can be used to modify the microstructure to redistribute the stress, so that the mechanical properties of the weld nugget improves significantly. right? It's clear, the enhanced weld thermal cycle, isn't it? Good. So why is it pulsing here? Because of the alternating current. Okay, so we always use an alternating current that is preferred for resistance welding. Okay, good. So in order to summarize the enhanced weld thermal cycle, so we can apply a pre-compressive force to set the electrodes or peaks together, no? So that's a skews time, right? Then we can apply preheating to reduce the thermal gradient at the start of the weld timing, or to, for example, to soften any surface coating is there, right. So once you apply a preheating, so you can also minimize the temperature gradient, and then you can apply a forging force to consolidate the nugget, and then you apply a weld thermal cycle, the actual welding time, and then subsequently you can do a post pulsing for quench and tempering, right. It's clear. And you may also play around with the current decay, especially in aluminum alloys, to prevent hot cracking. Aluminum alloys are, extremely notorious to weld by resistance spot welding. Okay, resistance spot welding of aluminum alloys, and also the stainless steels. Stainless steels are nightmare to weld in resistance spot weld. So I never seen someone welded resistance spot welding of stainless steel without cracking. Okay, so stainless steels are reasonably good material if you are using a GMAW or GTAW to weld, because you can play around with the solidification pattern, solidification method. You can play around the dilution, so that you can avoid hot cracking. But here there is no way you can add a filler. Okay, so it's all autogeneous weld. So if you are doing autogeneous weld, and the stainless steel and aluminum alloys, they are prone for cracking, because you also apply a load. Okay, so compressive load becomes tensile in one axis. So in that case, in aluminum alloys or stainless steels, they are really prone for cracking, and they also have a thick oxide coating, isn't it? Oxide layer, aluminum as well as stainless steel. So the contact resistance can be huge. Okay, so because of this presence of oxide layer, so you may end up heating a lot, right. So you need to play around with the current decay or the downslope of the current in order to retard the quenching of aluminum alloys, which can otherwise lead to cracking. Okay, it's clear. So we can play around with these parameters to achieve required the weld metal properties. Good. Any questions on this? It's extremely important to understand this, because when you are doing a resistance spot welding in industry scale, you'll all, so these terms are very quite common. Skews time, for example, post pulse time, number of pulses. Okay, so we always tell the welding time in terms of cycles. Okay, so suppose if you tell that 10 cycles welding time, and you are using a 50 hertz AC. So what will be the welding time? So 10 cycles means, so 50 hertz means what do you mean by that 50 hertz in AC? 50 cycles in 1 second, isn't it? In 1 second. So the 10 cycles would take come on guys, 1/5, isn't it? So 1/5 times, that's a time required, that's a welding time. Okay, so if you look at you go to automotive industry, what is the welding time? They will take 10 cycles. Okay, so because the 50 hertz is the most commonly used the current, so the welding time is always measured in cycles. Okay, so we will say 10 cycles of welds, 10 cycles in 50 hertz, right? It's clear? Good. So this is a typical again the schematic of the equipment. So before going to this, we also have such equipment in our lab. Okay, so this is the industrial scale resistance spot weld. So what is over here? Can you see clearly the picture? Okay. So, this is the cantilever which also has the water inlet. Okay, so water inlet, water outlet. So, water inlet, water outlet. So, that is to cool the electrode, and you see here these two, they are the electrodes. So, now the sheet is not there. So, it is placed between the electrodes, right, and the load is applied through this cantilever. So, we have some hydraulic. So, these hydraulic mechanisms, isn't it? So, this hydraulic apply a load required to keep the interface in contact, and subsequently the electric current is passed, and then water cooled the electrodes would pass the current between the fairing interfaces, and then you form well nugget. Yes, it's clear? Okay, good. So, if you look at the schematic of this such setup, and this is industrial scale resistance spot well. So, in a for example, in automotive platforms, and these arms would be replaced by robots. Okay, so these arms will be replaced by the robots. Okay, so in this case, in our lab, so we have a simple cantilever beam, so used to make the well nugget. So, this is a typical single phase AC spot welding circuit. So, we have a transformer. So, in this transformer is somewhere over here. Okay. So, and then you have a horn, the flexible conductor, which is used to apply a load, and this is a typical depth, and this is the cantilever beam I was talking about, and the water cooling goes in and comes out, and then the interface, welding interface is kept between the electrodes, and then while applying a load we can pass the current, you form the well nugget. Yeah, it is a simple schematic. It's clear? So, we can play around with so nowadays this transformer circuit is also microprocessor controlled. Okay. So, we can also play around with the ramping time, cool down time, post pulsing, number of pulses, okay. So, load and squeezing load and then cooling load. So, everything can be varied based on the program what we use. It's clear? Good. Okay. So, this is the mass effect I was talking about. Okay. So, it is very important. So, in order to calculate the amount of heat or energy needed to heat up a material, so typically you want to heat up from room temperature to close to the above melting point, right. So, then how do you calculate how much current you need to achieve a required well nugget diameter? You can use a simple physical law.
So, the
yeah.
M here is the mass of the nugget?
It is the mass of the nugget. So, how do you calculate? So, mass of a nugget can be calculated from the volume and the density. Okay.
Density we will know, but
So, mass we assume, for example, you know the well nugget diameter, right. Suppose if you want to achieve well nugget diameter, something like that. So, I am drawing a cross section. Okay. So, this is a cylinder what you form basically, isn't it. So, once you have to know the well nugget diameter, required well nugget diameter, and then the height of the cylinder will be the thickness, combined thickness, isn't it.
it is under the root 4 root D equal to 4 under root.
Yeah, that is also you can assume. So, for example, you can also say this is the top view and this is your well nugget diameter, and if you look at the side view you do not see unless you do a cross section, isn't it. Yeah, because the electrode is placed somewhere here like this from the top, right. So, the well nugget diameter, for if you want to get a required well nugget diameter, how much current you want to send for a given time, how do you calculate. So, you know the height of the cylinder, which is the combined thickness of the plate. So, you want to know the diameter, okay. So, then you solve for the cylinder volume, okay, and then you get m from that. You can, once you know the m, so you can calculate q. So, once you know the q for a given welding time, how much current you need, that you can calculate, isn't it. So, that is a simple, right. So, only trick here is the R. The R here is made of 4 components, isn't it. R1, what is R1? electrode resistance, R2 seat resistance or the base material bulk resistance, R3 is the contact resistance, okay. The R4 is resistance between the interface and the electrode, okay. So once you know the resistance, basically we always assume the contact resistance is the maximum. So compared to contact resistance, other resistance are negligible. So once you measure the contact resistance, so we can calculate the current required to form a given well nugget diameter, okay.
So
Yeah.
Here R should be the contact resistance,
Yes,
not any other one.
R is the contact resistance, we can assume
Only the contact resistance.
only contact resistance, yeah. So because say the contact resistance will be 100 times more than the bulk resistance of the plate as well as the copper electrode, okay. And the resistance between the electrode and the workpiece, it is also negligible because the heat is extracted by the water, by the cooling, that is not contributing the nugget growth, okay. So only resistance that is actually controlling here is the contact resistance between the sheet, okay. So once you know that, and that can be calculated again by using a simple bridge circuit, right. So once you know the contact resistance for a given load, okay, and then we can measure the current required for a given welding time to generate a well nugget diameter of so and so, right. It's clear. So in experimental point of view, we don't really like to make it life easy, so we will measure experimentally what you known as weld growth curves. Okay. So I will come back to that. Okay. So this is the weld growth curve because you asked the question. So basically the weld growth curve is we develop as a function of current and welding time what is the weld nugget diameter. Okay, in this case I plotted strength is proportional to the well nugget diameter, okay. So if you look at the well growth curve, so you plot as a function of current or a welding time. So either we fix a current, vary the welding time, or you fix the time, vary the welding current. So both will lead to increasing weld nugget diameter. Isn't it? Because I square R T, either fix T vary I or fix I vary T, and both will lead to change in nugget diameter, okay. So this is typically will be like this, okay. So there is a maximum current, okay, so that is I max. So ideally the thumb rule is to achieve an optimum strength, we always use the thumb rule of 4 times square root of thickness. So if the thickness is 1 mm, well nugget diameter should be 4 mm. So that is the typical. So why 4 mm? So because we can cover the entire cross section, okay. So that is why it is 4 mm. So if you have an ideal, yeah, you can identify now. So what current and time is needed to achieve a well nugget diameter of our interest. So we cannot keep on increasing the current because upon I max, you have a more liquid formed and you are applying an excuse force, the liquid would start splashing out, isn't it? So you form a liquid and you are applying compressive force. So then if you have the electrode applying a pressure and you have a sheet, okay, and if you start melting and if you make a large amount of liquid, then you apply pressure, then liquid cannot withstand the load, isn't it? So then it will start splashing out, and this is known as expulsion or splashing, okay. So upon increasing current to a certain level, you observe splashing and then you won't form well nugget, you will just have a cavity, okay. So the I max is the maximum current above which the splashing occurs, right. So generally we don't operate until I max. So we will operate much below I max, but we will have to know when I max is happening. So these well growth curves can be plotted as a function of time by constant time and the varying current, identify when is I max, and then we can choose the Willingham diameter which is required by the standard. Okay, it's clear, and you can also calculate from the physics. So, what I and T you have to get for a given m, Cp is fixed and m is from the thickness, right? It's clear? Yes or no? This is simple, right? Simple balance. Good.